Good morning. Before we start, I'd like to remind you that today we are going to finish this chapter, and the first homework assignment on mastering physics about this chapter is due this evening. So please keep this in mind. We continue our discussion of electric fields and forces. What we learned so far is that electric charge is an intrinsic property of matter that determines the behavior of matter with other matters nearby or even at a distance. This intrinsic property is similar to mass with one difference. Mass is always positive or zero, while charge can be positive, zero, or negative. Then we learned how to use friction or induction or conduction to charge objects. We learned also that two important properties associated with charge are: first, charge is conserved, so you cannot create it from nothing. And the second property is that charge is always quantized, which means it exists as integer multiples of a fundamental quantity that we call the quantum. We learned that the quantum of charge is E, the charge of the electron. And this charge is equal to 1.6 multiplied by 10 to the minus 19 coulomb. Coulomb is the unit used in the SI system to measure charges. Then we learned that point charges act on each other by mutual forces that can be attractive if the charges are not similar, and the forces can be repulsive if the charges are similar in type. Coulomb discovered this important law that you can see now on the screen, and this law, as represented by this equation, tell us that the force is directly proportional with the product of the charges and inversely proportional with r squared, where r is the separation between the two charges. So as you can see in figure A, the forces are repulsive because charges are both positive, while in figure B, the forces are attractive because the two charges are different in type. According to Newton's third law that we learned in Physics 1, for each action there is an opposite reaction equal in magnitude. So obviously, these forces are equal in magnitude, though they are opposite in direction. The proportionality constant K is called the electrostatic constant, and when we use SI unit, it is equal to 9 multiplied by 10 to the power 9 Newton meter squared per coulomb squared, and it can be represented sometimes using the permittivity of free space constant, K equals 1 divided by 4 pi epsilon naught. Things to remember when we talk about Coulomb's law is that the law applies when you have point charges. If you have extended objects, then you will need another treatment in order to calculate the electric effect. In this lecture, we are going to continue to learn how to study the electric effect deeper, starting with Coulomb's law, and go deeper by introducing the concept of the electric field. But before that, I'd like to check your understanding. Use your clicker, read this problem, and now we start. You have 1 minute to respond. I will give you 10 more seconds. Yeah, you got it right. It is C. We start with the second one. I am having some difficulties with the clicker. So this is the problem. Five seconds. Yeah, you got it right. That's good. It is B. Very well. So from your response, from your feedback, I'm glad I can see that you have good understanding of the concepts that we have covered so far, which means we can now move safely to the new concept, the concept of the electric field. The concept of field in physics is an important concept. The first field that you have studied in Physics 1 was the gravitational field. The gravitational field, if you go back and recall what you learned in Physics 1, tell us that Earth generates a field, gravitational field, through which it acts on various objects and attracts these objects toward the center. The field can act over a distance. For example, Earth attracts Moon by this gravitational field. So now in this course, we extend this concept, but now instead of talking about the gravitational field and the planet Earth, we are going to learn about electric field that is generated by charges. So instead of saying a charge acts on another charge and using Coulomb's law to calculate the force, now we will say that a charge or a group of charges created a field, and that field acts on any charges once the charge is in the premises of the field. So it is a development of the concept of Coulomb's law. But as we will see, it allows us to do more. We define an electric field by this equation, E equals F divided by Q. So it is simply the force per unit charge. The force per unit charge. So in figure A, at this point, if you would like to see what is the electric field, you need to place a charge at that point and then see the effect, the force acting on that charge, divide the force acting on the charge by the charge in order to get force per unit charge, and force per unit charge is simply the electric field. You can write this equation in another form. Force equals QE. Force equals QE. So once you know the charge and you know the electric field at the location of the charge, you will be able to calculate the force. As you can see in figure B, if the charge is positive, then the field and the force are parallel. They have the same direction. While, as you see in figure C, if the charge is negative, then the force and the electric field are opposite to each other. In fact, you can predict this behavior by just going to the equation 16.5. F and E share the same direction if Q is positive, while if Q is negative, then you will get a minus sign, which means E is opposite to F. From this defining formula for the electric field, the unit of electric field is a unit of force divided by a unit of charge. So Newton per Coulomb. This is the SI unit for the electric field. So according to this new approach, in order to calculate the electric force acting on a charge at any point, all what you need to do is calculate the net electric field at that point, and then apply this equation 16.5. Force equals QE. Once you know E, you know Q, so now you know the force. So the method that you need to follow in order to calculate the electric field is simply use Coulomb's law first in order to determine the force, then divide the force by the charge Q, you get force per unit charge, and from there you end up by this equation, E equals KQ over R squared. I want you to examine this equation for a minute. What is in this equation for the electric field? There are two things. You have Q and you have R. You have two variables. So for any field, you will need a source to generate that field. The source in this case is the charge Q. And the field depends on the location. This is the meaning of having R in the defining formula. The field depends on the location. Go back to physics 1. Gravitational field depends on location. The acceleration produced by the gravitational field is 9.8 meters per second squared. That is at the sea level. While if you go to high mountains, it will be less. If you go away from Earth, like in a spaceship, it will start decreasing until at some point it fades away, goes to zero. So yes, fields in general depend on location, not only electric field, all fields, electric, gravitational, magnetic, you name it. They all depend on location. In order to understand how to solve problems of electric field, I selected this nice example. We have an isolated charge of 15 microcoulomb in vacuum, and we need to find the field at point P, at this point here, at the mouse cursor. We need to determine the electric field. To do that, we bring a small charge, we call it test charge. We use a test charge in order to measure the field. So Q naught is a test charge. The distance between point P and the source of the field, the original charge here, is distance R. It is 0.2 meters. Okay? So now, in order to determine the electric field at point P, we need to calculate the force between the source of the field and the test charge, and then we divide the force by the test charge in order to get force per unit charge. Force per unit charge. So we use Coulomb's law. The force is equal to the product Q naught divided by R squared, the whole thing multiplied by the electrostatic constant K. When you plug in the numerical values for K, for Q naught, for R, this is your force. It is 2.7 Newton. 2.7 Newton. This is the force. Now, to determine the field, you need to divide this force by Q naught, such that now you have force per unit charge. Force per unit charge, okay? So you divide 2.7 Newton by this test charge, and you get the result 3.4 by 10 to the power 6 Newton per Coulomb. And the direction of E is the same direction of the force because the charge is positive. The charge Q, which is the source of the field, is positive. Therefore, the direction of the force and the direction of the field are parallel. They are the same direction. Now, to check your understanding, think a little bit. What will change if Q was negative? What will change if this Q, the source of the field, was minus 15 microcoulomb instead of plus 15? What will change? The only thing that will change is the direction, right? So now the field, as you can see in figure C, the field still have the same numerical value, 3.4 by 10 to the 6, but now it is going into the charge. This is an important piece of information. Yes? What is 8.99? Oh, this is the test charge. Yeah, let's go back to Coulomb's law. In Coulomb's law, you have Q and you have Q naught. A Q is 15 microcoulomb and the Q naught is 0.8 microcoulomb. It is the test charge. Yeah, that is, yeah, I see. Yeah, that's wrong. It's not 15. This should be 0.8. Thank you for pointing to that. This is a good point. So now, whether it is 15 or whether it is 0.8, the important thing that it cancels out because you multiply by 0.8 to calculate the force, and then you divide by 0.8. Your final answer does not depend on the value of Q naught. Thank you for picking this one. Okay? So the electric field does not depend on the test charge. The electric field is a property of a Q. Because of that, we call Q the source of the field. The source of the field. Each field has a source. Now, if Q was negative, as in figure C, then the electric field now is going into the charge. Instead of going out, now it is going into the charge. So in this case, we call the charge, we call it. So any electric field will require either a source or a sink. If the charge that generates the field is positive, then it is a source. The field lines will be going out from the charge. If the charge is negative, then field lines will be going into the charge, and the charge will serve as a sink to the electric field. If you have several charges and you are asked to calculate the electric field due to these charges, you need to apply the superposition principle, which means you calculate the field due to the first charge, the field due to the second charge, to the third charge, and then you use vector algebra to find the resultant electric field. You superimpose these fields for various charges in order to get the total field E. Once you determine the total field E, you will be able to calculate the force on any charge within that field. This example helps us to understand this concept of superposition. We have two positive point charges, Q1, 16 microcoulomb, Q2, 4 microcoulomb, separated in vacuum by a distance of 3 meters. So this is the distance separating Q1 from Q2. Find the spot on the line between the charges where the net electric field is 0. Since electric field is vector, then yes, you may get a value for the field equals 0. So the field due to Q1 is positive, so it will serve as a source, and the field will be going out, as you see in this vector, E1, and the field due to Q2 also will be going out of Q2, okay? Q2 is positive, so it will serve as a source for the electric field, not a sink. So if we assume that at some point, like point P here, the two fields are equal in magnitude, opposite in direction, field can be 0. We don't know the location of this point. We don't know the location of this point. However, we know that this point should be located on the line connecting the two charges. Why? Because from vector algebra, as we see in this illustrative figure, if the two vectors are anti-parallel to each other, then yes, they may cancel each other. While if you pick any other point, like here on the mouse location, if you pick a point here, the two fields are not opposite to each other, so they will never cancel. So the only place where electric field may cancel is along the line connecting the two charges. In order to identify the location of this point P, let us assume separation between the point and the Q1. Therefore, the separation between Q2 and the point is going to be 3 minus D. And then we calculate the electric field E1 and E2 and make the two fields equal, as you can see here in this slide. So, in general, the electric field equals KQ over R squared. And now we are interested in the magnitude of the charge because we already used the free body diagram. We identified the direction. Now we deal just with magnitudes. We require that E1 equals to E2 in magnitude in order to come. So E1 equals KQ1 divided by the distance squared by D squared. And E2 equals KQ2 divided by the distance squared. The distance is 3 minus D. So now you need to solve this equation. If you divide both sides by K, K cancels out. When you simplify, you end up with this equation for D. You have one unknown. The easiest way to solve this equation is to take the square root of both sides. Simplify, you get finally this value for D. So D equals 2 meters. D equals 2 meters. The point is located 2 meters to the right of Q1 or 1 meter to the left of Q2. At this point, the two fields canceled each other, and the net field is 0. If the net field is 0, this means if you put any charge there, it will feel no force, because there is no field at that point, right? This is the consequence of having 0 field. So electric fields for point charges start from the positive charge and ends at the negative charge. If you have, instead of point charges, if you have two parallel plates, this is what you expect to get. Electric field lines will be moving from the positive end and entering into the negative end. Like here you have two parallel plates like this, we call them capacitor. If you connect the first plate on the left side to a positive electrode of a battery and the other plate to the negative electrode of the battery, you will generate an electric field that will have this shape. We call these the field lines or the lines of force, okay? So for 2-point charges, it is just one simple line. But when you have charged plates, you have more than one line. You have infinite number of lines, in fact, representing that field. This is called monopole. Mono, Greek word, means one, okay? So instead of saying one charge, we say monopole. For a positive charge, this one, in figure A, field lines starting at the point and going out in all directions. The charge here serves as a source for the field lines. And in figure, we have a negative charge. So now field lines go into the charge. The charge serves as a sink. Field lines sink in the charge. Again, field lines follow radial direction, but instead of being out, as was the case with positive charges, now they are going into the charge. This concept of field lines help us to picture the field. The highest the density of these lines, the stronger is the field. If you bring two monopoles, one negative and one positive, near to each other, you create this structure, which we call it a dipole. Di, again, is a Greek word. It means two. So instead of saying two poles, we say dipole. Dipole. I'm sure you have heard of this word before. Dipole, right? You have dipole antenna. The cell phones that you use has a dipole antenna built in within the frame of that cell phone. Dipole antenna allows the phone to pick calls, to pick signals. Okay? That's another story. We may come to it later. But now I just wanted to mention that when you have two monopoles, one negative and one positive, near to each other, you will get a dipole. So now you need to superimpose the field lines. When you do that, you get this structure. If you examine these field lines, you will see that none of them overlaps with any other line. The field lines never overlap with each other. Okay? They all start from the positive charge and ends into the negative charge. The direction of the electric field at any point, like point P here, you get it by drawing the tangent. If you draw the tangent to this field, then you will get the field. In your first lab, you will learn more about the electric field. Okay? This is a demonstration of the electric field that I'd like you to watch. So here we are trying to create a structure like parallel plates. So each one of these two parallel lines represents a plate. It is connected to a potential difference, a source of charges. You can think of it as a battery, for example. So one end is negative, the other is positive. So now, when you put the source on, we are using semolina seeds and castor oils. So now the seeds will align themselves parallel to the field lines. As you can see, the seeds that were random, now they are parallel to illustrate the fact that field lines are parallel between the two electrodes. Strategy to solve electric field problems. You need to sketch a diagram to show all charges in the diagram with the signs, and then to follow the convention that lines going from positive charges will be going out, lines for negative charges will be going in. Then you apply Coulomb's law for every single charge, and once you have the vectors representing these forces or these fields, you need to apply vector algebra to superimpose the forces if you are interested in electric forces, or superimpose the fields if you are interested in the electric fields. That's it. To summarize, we can say that field lines are considered like signature for charges. Wherever there are charges, there will be field lines. The magnitude of the electric field is proportional to the magnitude of the charge, and usually this is expressed by the density of lines, the number of field lines per unit area. We call it density. The density gets greater as the magnitude of the field gets stronger. The third point to keep in mind always is that for positive charges, the electric field line starts there, while for negative charges, the field lines end there. For this reason, we call positive charges sources, while we call negative charges sinks. Now, think of a conducting shell. Think of a metallic shell, as you see in this figure, and at the center, you have a monopole. You have a positive charge. What will happen? Field lines will start at the surface of the charge in all directions. Once a field line reaches the surface of the conductor, it will act on the charges within the conductor. Remember that for conductors, there are always free charges moving in randomly. But now, those random charges will start aligning themselves according to the electric field, because the electric field generates electric force. As a result, negative charges will move opposite to the field, while positive charges will move parallel to the field. So, the total charge within the conductor remains constant, remains zero, remains neutral as it was at the beginning. There is no charge within the conductor itself. But this zero is split into two halves, -1 on the internal surface of the shell and positive on the external surface of the shell, and this is simply as a result of the electric field. At equilibrium, remember this is electrostatics. Electrostatics means we are dealing with electrostatic equilibrium. There is no motion. At equilibrium, the charges will redistribute themselves such that the internal surface of this metallic shell will be negatively charged and the external surface will be positively charged. To achieve equilibrium, no motion, the net field within the conductor must be zero, because zero field means zero force, right? This is achieved by having the field due to these charges within the conductor. This is positive, this is negative, so the field is opposite to the field due to the source here. So the two fields cancel each other within the conductor. When they cancel each other, then the net field within the conductor is zero. The net field is zero means the net force is zero, so now equilibrium is established. Equilibrium is established. No charges are moving. If you move any charge, this means you disturb equilibrium. We are not in electrostatic equilibrium, okay? What we understand from this simple discussion is that at equilibrium, the electric field inside any metal is zero. However, at the surface, at the outside surface of the metal, you will have equal amounts of positive and negative charges such that they produce a field opposite in direction and equal in magnitude to the original field, such that they cancel that field and produce zero field within the conductor. How about the surface? Suppose you have a good conductor, as you see in this graph, and there are charges at the surface. So the question is, what would be the direction of the electric field? What would be the direction of the electric field due to these charges? We start by assuming that the electric field could be at any direction, okay? But when you decompose that field into vertical components and components parallel to the surface or horizontal components, the horizontal components will cancel with other horizontal components from other neighboring points, and the only component that will survive is the perpendicular component. So we end up with just fields that are normal to the surface. Whenever you have any surface, any conducting surface, the only electric field that will survive are the ones normal to the surface. Applications of electric field are everywhere. In your textbook, they picked two examples, one for the DNA and another one about photocopying machines. The DNA, as you may know, contains hydrogen, oxygen, carbon. These are the organic elements, the organic atoms that together creates the DNA. Within the DNA, we have the so-called hydrogen bonds that will determine the attraction between various atoms in the DNA. So you have the atoms represented by T, thymine, and the ones represented by A, adenine. You have cytosine, C, and you have guanine, G. The attraction between these molecules of the DNA is electric. So each molecule is a field. You may simplify this field into a dipole at the end, and these dipoles interact with each other and give the DNA its structure, which is a dual helix. In fact, electric forces are responsible for the structure of the human body, our body. You have all kinds of electricity, okay? The blood has charges that are in motion. We call it the plasma, okay? You have ions, calcium, potassium, sodium, etc. And all these charges has to be in a predetermined amount that keep us in good shape and healthy. If any concentration is disturbed, then you have illness. So it's not only the DNA. Photocopying machines, as you can see in this illustration, you have a drum charged positively, and then the image for the letters focused on the drum, like here, the image of letter A. Then black areas stay charged, and other areas will lose the charges. So the image is transferred to paper and sealed by heat. So this is paper, and this is heater, such that the image that was deposited on paper will now stay there. For laser printers, it's the same thing, but now the beam of light is laser. The original beam of light, the laser beam, is controlled by the computer. Another way to calculate the electric field instead of Coulomb's law is to use Gauss's law. But we are out of time, so I leave this for you to read.